I have a handout I did that if you're taking this course from me, you'll get it by email, I'm sure. Um, the first page says number of steps to fill in 4 boxes chosen at random, and at least the copy I have right here has the same chart printed twice. I can't remember why that happened. Only one of these charts is good enough, the same chart. Alright, so I want to explain this example, and so hopefully you've got this in front of you. Makes some sense. Some years ago, I had a Math 290 course. Math 290 is called Research Topics in Pre-Calculus. It's where the students work together on various kinds of long-term problems. They might spend up to 2 weeks working on a math problem. And very interesting stuff that you don't find in textbooks. Anyway, one year I challenged them to solve this problem. And let me start off small. I want to explain this to you, how all this works, before I get to the statistics. Suppose you had 2 boxes, and you pick one at random. Suppose you pick this one. We'll color it in. Alright, now let's pick another one at random. Now, the chance of getting this box is 1/2. So half the time you would pick this box at random, the other half the time you would pick this box again. And so, so suppose you make your next choice, and if you get this box again, then you make another random choice, and eventually you're going to fill in this box. So it's possible to calculate the average number of choices it takes to pick both boxes at random. All right. Well, so I asked my class to calculate that, and of course we made it a bigger problem. We said, well, what about 3 boxes? And then what about 4? And we got up to 5 boxes, and that became a huge calculation, and we kind of gave up after that. So, but now I saw this. I got this idea some years ago from a math conference I went to, and where a mathematician from I think it was Penn State worked out this question. If you had a certain number of boxes and you chose them at random, how long would it take for you to hit every box, to have hit every box? And he figured that out. Now I don't know how he did that. I don't recall how he did it. It's pretty high level math, out of my area of specialty. But I have programmed this as a simulation in my computer. I used to run it. I think at the time my laptop could have 1,000 pixels across and 700 pixels down. So imagine a box with 1,000 small boxes across and 700 down. 700,000 boxes. And when I ran the computer program, it would pick pixels at random and color them in. It would color them blue. And if a pixel got chosen again, it wouldn't change color, it would just stay blue. And so as you ran this program, you would see the box gradually fill in with blue dots, and then near the end it would be almost all blue except for a couple little white spaces, and then they would gradually blink out. I had it programmed also that when it was done, it would print out the number of steps, number of random choices it took to fill that in. Anyway, it would run pretty quick. So on that basis, I had a way, I don't have the current software to run that anymore, but I had a way to run this problem at random, literally run it for any size configuration I wanted. So to get to my point of this handout, I said, okay, let's go back to 4 boxes. And the game is this. Pick a box at random. Pick another box at random. Pick another box at random. Pick another box at random. Keep doing that until eventually you have chosen all 4 boxes. Record the number of steps it took, the number of picks or random picks it takes to fill in all 4. Alright, well, I ran this simulation on my computer 500 times. Okay, And the results are in this chart right here. So if you look on the chart, it's kind of it's interesting distribution. I have a histogram or bar chart, and it sort of follows this pattern. So if you look that up as a distribution in the book, it kind of resembles a chi-square distribution. And the mode was 6 choices. So, the minimum number you could hit is 4 in case, all 4 choices at random chose a different box, then 4 is the least number of picks it would take. Well, that happened, according to my chart, that happened around a little bit more than 11% of the time. Five steps, it took a little over 12%. 6 was the mode, it took a little over 14% of the time. And then it dropped off from there. And the most extreme simulation I ran in 500 trials was 26. It took, one time I ran it, it took the computer 26 times of throwing darts at those boxes to finally have hit all 4 of them. Alright, so I hope you have a clear idea of what the simulation is, and it produced a statistical distribution, which appears to be a chi-square distribution. Well, okay, now, when my class did this for 4, they were looking for the theoretical result, expectation. In theory, what is the average number of picks? And so really, by using theoretical probability and statistics, they were able to calculate the population mean. In other words, the answer, the population mean ends up being 8 1/3. So on average, it takes 8 1/3 attempts to fill in all 4 boxes. Now I realize that on the chart 6 is what came up most often, but if you were to average it out, it would come out pretty close to 8.33, 8 1/3.